Okay, let's do some cell-based coagulation. What we're looking at on screen is a little slice through some vasculature, and primary hemostasis has happened. So what we can see on screen here is that it doesn't matter whether this is arterial, because we've got indirect binding of our platelets via von Willebrand factor binding to platelet glycoprotein 1b, or it doesn't matter whether it's in the venous low flow, low shear system, where we've got direct binding of the platelet using platelet glycoprotein 1a or platelet glycoprotein 6. Bottom line is, this platelet is tethered, and what we should really do is say, rather than this being fibrin, it should be fibrin O-gen. Okay, fibrinogen. Now, what we need to do is to convert this fibrinogen into fibrin in order to properly tether, these platelets. Let's move this back here. But as yet, we haven't done that. So we now need to go ahead and talk about what it is that's going to be happening to make all of this work. And the answer is found over on this bit of the diagram, where we've got some denuded endothelium, and you can see that there's no endothelium here, but there is here. And underneath, you can see we've got the vascular smooth muscle, and this vascular smooth muscle is expressing in yellow this tissue factor. So what we find in our vasculature is that we've got factor 7 in its inactive form, and what's going to happen is this factor 7 is going to bind to this tissue factor, and it's going to make a complex, and this complex is the tissue factor plus 7a, because the binding of the tissue factor causes the 7 to become active, the tissue factor 7a complex. Now, this complex is called the, where shall I write this? Over here. Extrinsic 10A's complex. The extrinsic 10A's complex, and it's going to do two things. The first thing it's going to do is it's going to do its job, 10A's, so it's going to turn factor 10 into its active form of 10A, and the other thing it's going to do is it's going to activate coagulation factor 9. Okay, so at this point, what I'm going to do is I'm going to rub out that, and I'm just going to say 10A, like that. I'm going to put a little thing around there as well. Now, the fact that I've drawn this 9 so close to this platelet doesn't mean that it's bound to the platelet. There's going to be some binding to platelets that happens in a minute, but we're not there yet. What this 10 is going to do, this 10 is going to activate coagulation factor 5 into its active form, which is 5A, and then these two, the 10A and the 5A together, are going to form a complex. So we'll do 10A plus 5A, like this. And this complex is called the prothrombinase complex. So the prothrombinase complex, it shouldn't take a rocket scientist to work out, is going to activate coagulation factor 2, prothrombin, into its active form, 2A. Okay, so once again, we'll just rub this bit out like that, and we'll just put a here and say 2A, like that. Now, this 2A is going to do some important stuff. Actually, we can make this even better, because we can say that everything up to this point represents the first phase of cell-based coagulation, which is called initiation. Initiation phase. Now, the next bit, from the activation of prothrombin into thrombin, this is going to form another phase of coagulation. And this activation of thrombin is going to do a couple of things. One, it's going to turn 5 into its active form, 5A. The next thing that it's going to do is it's going to turn 8 into its active form, 8A. And it's going to turn 9 into its active form, 9A. Like that. Now, I suppose the question is going to be, well, why? Why does this happen, and why isn't it happening all the time? Why aren't we just all suffering from disseminate intravenous coagulation? And the answer to that lies in change our color to red, make my text a bit smaller, that we've got standing in the way of this part here is an inhibitor, and it's called TFPI, which stands for tissue factor pathway inhibitor. Because if you think about it, in the old in vitro version of coagulation, we would have the intrinsic pathway, and that would be from coagulation factor 12, a load of mess happens, down to the activation of coagulation factor 10, and we would have the extrinsic pathway. And that would be from tissue factor plus 7A to an active factor 10. So the easy way to remember this was in the intrinsic and the extrinsic pathways were renamed the contact factor pathway and the tissue factor pathway. So what we've got over here, tissue factor plus 7 activates 10. That's our tissue factor pathway. So TFPI is tissue factor pathway inhibitor. So what we need in order to get lots and lots of our thrombin activated is we need to overcome that tissue factor pathway inhibitor. So you need vascular damage that is going to be great enough that it's going to be generating thrombin over and above what tissue factor pathway inhibitor can inhibit. Cool. So we've activated our thrombin, and we've generated 5, we've generated 8, we've generated 9, and we've generated them in decent amounts. So this bit here is not the initiation phase anymore, but it is the amplification phase. So after the amplification phase, we're going to move on to the next phase, which is called propagation. Now, this is where things start to get quite interesting. So what's going to happen between the amplification phase and this next propagation phase is that where coagulation happens changes, because at the moment this is kind of the initiation and amplification is happening in and around the open vasculature. As that's happening, what we're doing is we're forming more and more and more of a platelet plug. And what's going to happen is the focus, or where the coagulation is happening, is going to shift from the vasculature to the platelet. So what happens is this 8 that we previously generated, so this 9 that we'd previously generated, can't read my Roman numerals, and this 9 is going to come together and it's going to move to the platelet. Just there. As is this 8. And they're going to form a complex. And that complex is important. So it is zoom in a bit, it's the 9 plus 8 complex. And that complex is going to activate coagulation factor 10. So this is the intrinsic 10A's complex. So the I-10A's complex. So the intrinsic 10A's complex. So we've now generated a load of new factor 10. In the meantime, this factor 5 over here is going to migrate to the platelet surface, and it's going to complex up with that 10, and we've already met this. That's the prothrombinase complex. Now, there's 2 key things to talk about. Number 1 is that this intrinsic 10A's complex is about 50-fold more efficient at producing 10 than the extrinsic 10A's complex. 50-fold. So much so is its efficiency good, and that 90%, okay, 90% of all of your factor 10 comes from this route. 90%. Let's actually do a good job of this. 90% of all XA comes from the intrinsic 10A's. Okay, so the intrinsic 10A's complex is where it's at, and that is going to generate massive amounts of this prothrombinase complex. Now, it's going to generate this massive amounts of this prothrombinase complex for a couple of reasons, right? Number 1, chief among them, is that the 10 and the 10 which is inactive and the 10A's is anchored to the platelet. Sorry, got a frog in my throat. Plate. So they can't go anywhere. Okay. It's also worth pointing out that this requires calcium as well. And actually, if we're going to be complete about this, it's worth pointing out that this needs calcium as well. So the fact that this is anchored is a big thing. It's anchored to the platelet, which means everything is held in place. It's all where it needs to be. Okay? So 90 is 50-fold more efficient. 90% of your intrinsic 10A's is going to be produced from this route. Great. What's happening with the 10? So the 10 is anchored to the platelet. The 10A's is anchored to the platelet, which means we go lots of 10 getting converted into lots of 10A. Now, the other thing is that 5A is going to migrate to the platelet surface, but it's also going to meet factor 5 from the alpha granules of the activated platelet. Now the 5 that is coming from the alpha granules of the activated platelet is partly active already. So it's already partly activated, so it's just waiting to come into contact with the 10 just to finish the job. So this prothrombinase complex is going to go ahead and do what it does. It's going to take 2, lots of it, and convert it into lots of 2A. So this thrombin that we're now producing has got several functions. Okay? It's got several different functions. Let's just zoom out on that. So the amplification phase looks like this. The 2 producing loads of 2A, so lots of prothrombin producing lots of thrombin, and it's going to do a couple of things. Number 1, it is going to go ahead and is going to activate more, so this is a positive feedback loop, factors 5, factor 7, factor 8, factor 9, do this properly, factor 9, and factor 13, which we'll come to in a minute. The other thing that it's going to do, so it's got that feedback loop, so we'll represent this by going like that and saying it's feeding back in. Number 2, it's going to take factor 1 and convert it into 1A. So it is going to take fibrinogen and turn it into fibrin, which is kind of the whole point of it, really. So we want to take, and actually we can do this. We can go and just remove that fibrinogen from there, and then we can put a big thing around that and go fibrin 1A. The factor 13 is going to go ahead and cross-link that fibrin to other fibrins, and it's going to stabilize our platelet plug. The next thing it's going to do, it's going to activate protein C, but that's for another video. It's going to activate something called activate TAFI, which stands for thrombin activatable fibrinolysis inhibitor. So it's going to ramp down our clot breakdown process. And then the other thing that it's going to do, 5, promote tissue repair. So zooming that back out. That, like this, move that there. That is our amplification phase. This is the propagation. That is cell-based coagulation. I hope you find it useful.